Hello friends, welcome back to my channel, a Buddhist physicist. So today I'm going to talk about the book that I mentioned in one of my previous short videos, the book on quantum theory by David Bohm. I have the book here, so just to refresh your memory if you had a chance to look at it. Okay, so this is a classic book on quantum physics written by late American quantum physicist David Bohm. So this is considered to be one of the greatest books written on quantum physics, and I'll talk a little bit about what this book is about and why is this so famous. So the purpose David Bohm had in writing this book was twofold. First was to explain quantum physics to people who wanted to learn quantum physics in easy to understand language. Quantum physics, as you know, is a notoriously difficult subject. It's highly mathematical and most people lose their way in the jungle of mathematics. So Bohm wanted a different approach. He followed a different approach. He starts out by describing in words what quantum physics is about, and then gradually he builds up the theory. So it's interesting to note that the basic equation of quantum physics, which is the Schrodinger's wave equation, makes its appearance after 185 pages in this book. So for over 185 pages he's just describing this new physics. It was new at the time. Why is it so different from the classical physics? What is so interesting about it? How it helps to explain the nature in a new light. So Bohm then builds up the theory and he provides all the mathematical apparatus and how to do calculations, for example, how to solve simple problems in quantum physics which can be exactly solved, like a particle in a quantum well. And then he moves on to more difficult and more advanced topics like perturbation theory. Indeed, this book was one of the best books to learn the perturbative theory of quantum physics for almost 40 years. So let me talk a little bit about what is perturbation theory. So most problems in quantum physics cannot be solved exactly. So what the best one can do is to approximately solve the problem, and one of very useful methods is the theory of perturbation. So Bohm explains in this book how to solve any problem that you might have perturbatively, which comes in two different flavors. One is time dependent perturbation theory, another is time independent perturbation theory. So for example, if one were to apply a strong electric field to a metal surface, then that field can enable an electron to tunnel out and to escape from the metal. So there you can use a time independent perturbation theory, and so using Bohm's methods one can apply this theory to solve that problem. Another example is to shine light on a metal surface, and that would cause photoemission. So this can also be handled using time dependent perturbation theory. In this case, the perturbation is time dependent, which is electromagnetic wave. So this is what Bohm explains, and if one wants to learn these highly advanced technical mathematical methods to solve problems in quantum physics, then this book is, I'm sure, in my opinion, is still indispensable today after 70 years. Of course, nowadays most of these problems can be solved by computers, and they are solved, but still the methods that are used, that are built inside the computer program, they are based on these theories. So it's a good idea to understand how these problems are solved. So what exactly is going under the hood? What's going on under the hood? So in the last two chapters of his book, in this great book on quantum theory, Bohm lays out what exactly quantum mechanics means. So see, the problem is that quantum mechanics, it's such a strange theory that ever since its birth, people have been arguing about what exactly it means to say that you are making a measurement, because quantum mechanics involves this. This is a very important part of quantum mechanics, that you can't really make a connection to the classical world unless you have made a measurement. So suppose, for example, an electron is emitted by some source, let's say a vacuum tube, and this electron is basically then strikes a screen. This is how an old-fashioned television screen works. An electron is emitted, and then that electron hits some point in screen. It emits a light, a point of light, and that's how an image is created. So this is the fundamental problem in quantum mechanics. What exactly it means to say that a measurement has been made on a quantum object, and this part of quantum mechanics has been vague ever since quantum mechanics was created 100 years ago in Europe by some of the greatest physicists who ever lived: Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. So these founders, they were able to describe the mathematical apparatus very, very accurately and clearly, and it actually works. So one can use the theory. But in the foundations of quantum mechanics, some things were left kind of vague, and one of the most important one is called the measurement problem. So the standard interpretation of quantum mechanics says that it makes no sense to talk about a quantum object before a measurement is made. Okay, one can do mathematical calculations about the object, okay, before the measurement is made, but what that object is, okay, what it physically means, that can only be done only after a measurement, and a physical measurement has been made. So for example, in the old-fashioned television tubes, I'm sure you must have seen these big televisions that they had, which had a vacuum tube in them, cathode ray tube, CRT. So electrons were emitted at the back by this cathode, this thermionic cathode, and then those electrons were accelerated and they would hit the screen, and the points where the electron would hit the screen would lead to a generation of a bright light, and that's how an image was created. So that example can be used to understand this measurement problem. So the question arises, what happens to the electron between the point when it's emitted and it hits the screen? Where is that electron? What is that electron? Is it a particle? Is it a wave? So that's what the Copenhagen interpretation of quantum mechanics, which was put in place by the great Danish physicist Niels Bohr and the great German physicist Werner Heisenberg. They said, well, don't worry about that, because you don't really know. Nobody knows what that electron is. Where is it? Whether it's a wave or a particle, whether it's delocalized, localized, it makes no sense to talk about it. The only point when we make a measurement, then we can say, okay, all right, this is where the electron hit, so it was a particle. So this is what Bohm talks about in the last 2 chapters of his great book. So he describes it in great detail, what exactly is happening to a quantum object before the measurement is made and after the measurement is made. So what exactly the measurement does, what's known as the collapse of the wave function, because before the measurement is made, the quantum object has a wave function. Wave function includes all the information about a quantum object. So once a measurement is made, that wave function collapses. So how all that happens, so that's what Bohm talks about in the last 2 chapters, and what he talks about there has remained one of the best description of the canonical description of quantum mechanics. Means one of the original and most widely accepted interpretation of quantum mechanics is the Copenhagen interpretation of quantum mechanics, like I said earlier. So if you want to really understand what Copenhagen interpretation of quantum mechanics means, then you really need to read the last 2 chapters of this great book. So that's all I have to say. I hope you found my lecture kind of interesting, and I hope you would go and look at Bohm's book, at least flip through it, and I hope you find something interesting to hold your interest. And your comments are always welcome at the bottom. Thank you.